Good afternoon. In today's final lecture of the course, we'll talk about carbon-13 NMR spectroscopy. Last time we talked about proton NMR spectroscopy, which is historically the first one and still the most commonly used spectroscopy techniques. If you think about proton NMR spectroscopy, it basically gives us information about a chiral skeleton only indirectly by looking at the protons that are attached. And since most of the action is actually happening on the carbons themselves, the question is, could we look at the carbons themselves directly? And the answer is yes, we could, and that's what is carbon-13 NMR spectroscopy useful for. Carbon-13 is also useful for establishing the identity of groups that don't have any protons attached to them, such as carbonyls or alkynes among the other groups. These two are the ones that we've seen so far. And so clearly there is a lot of impetus for developing, there was a lot of impetus for developing carbon-13 spectroscopy. However, this spectroscopy was also met with a lot of obstacles, the main one of which lies in the low abundance of carbon-13. If we think about the natural sample of carbon, this is 98.8% carbon-12, and then carbon-13 constitutes about 1.1%. and about 0.1% is radioactive carbon-14. Now carbon-12, because it has an odd number of protons and an odd number of neutrons, is NMR inactive, which is quite unfortunate because this is the most common isotope of carbon. Carbon-13 has an even number of, carbon-12 has an even number of protons and even number of neutrons. Carbon-13 has an even number of protons but an odd number of neutrons, which means it's NMR active, but there's 100 times less of it, so it's 100 times drop in sensitivity. This is the reason why carbon-13 spectroscopy did not take off at the same time as proton NMR did, because this had to wait for the development of powerful computers which were able to store information from often thousands of pulses, so thousands of individual spectra, which are then processed through the process of Fourier transformation to give us a carbon NMR spectrum. So that was not immediately possible in the early 60s when NMR was developed. Another reason, the main issue with carbon NMR is low sensitivity. Turns out that this low sensitivity comes in large part because of the low natural abundance of carbon-13, but also because of another more subtle factor, and that this comes from our relationship we already see, that the gyromagnetic ratio times H over 2 pi times B0. Well, the gyromagnetic ratio for carbon is just 1/4 of that for proton. Which means that this causes an even further drop in sensitivity of about 4-fold. So overall, carbon-13 spectroscopy is about 400 times weaker than proton NMR. However, which means that we typically need more samples, we need more constitutive samples to get these spectra. But once we do get them, the information that we extract out of them is very valuable because it gives us direct information about the carbons, and since a lot of these effects that occur in organic molecules happen on carbons, we get much more detailed information. In the next subtopic, we will see how our peaks positioned in carbon-13 NMR spectrum relative to the proton.